Welcome back, everyone. As the title implies, we're going to look at another example of computing the area of the three-dimensional surface. This particular example uses an old favorite of ours, the paraboloid that opens downward. We'll put some graphics in here in a moment. And we're going to look at the part of the paraboloid that is over a circular region in the xy plane. And just implies that z is positive here. So, we have our formula for surface area that we've been using. And the function g is the equation or function of our surface. So this right here is g of xy. That's g of xy. And this, as it implies, is the region which will have to do with our boundaries on the double integral. Now, for some visual aid. So we have ourselves the paraboloid. This is the z-axis here, and that's 9 units up on the z-axis. X and y axes are listed there. But we're not looking at the entire surface that sits on top of the xy plane. We're only looking at the part of the surface that's above a circle. Now, let me just slide it up a little bit. The circle in the xy plane is a circle of radius 2, and everything inside of the circle of radius 2, that's what this implies right here. All right. And it's not easy to see in the 3D picture, but it's sort of hinted at. There's a circle here, but let's look at it in a different way. We're looking at only the part of this shell that sits above a smaller circle. So you could kind of imagine that maybe it intersects about here. We're looking at the surface area of this top part of the cap of this parabola cone. Now, the setup's not too difficult. It won't be the hardest task that we've ever done. The x and y partial derivatives are not particularly difficult to calculate. Negative 2x is the x partial derivative, and negative 2y is the y partial derivative. So setting this up is relatively straightforward. The region of integration, we have to be focused on this circle when we're setting up the region of integration. So let me just sort of get us started here. Square root of 1 plus the x partial derivative squared would be 4x squared, and the y partial derivative squared is 4y squared. And then I'm going to go dy dx and hope that was not a bad choice when I started. Not difficult to switch this one around. So now the circle from left to right is from negative 2 to positive 2. So x goes from negative 2 to positive 2. Now the y boundaries are from the lower part of the circle to the upper part of the circle. Again, double integral region of integration is in the xy plane. We're not using this picture. The only aspect of this picture that's involved were these partial derivatives, and they're in here. That's the shape is factored into this calculation. These boundaries are for that circle. So if you have the circle x squared plus y squared equals 4, and you solve it for y equals, you get plus or minus the root of 4 minus x squared. So we have the negative boundary and we have the positive boundary, the lower and the upper. Well, if I only have to set it up, then I'm rather pleased with myself because it's set up. If you want to evaluate this, then you're about to partake in some trig substitution, followed by maybe one or two other fun little integrating techniques, and it might get pretty nasty with these terms here, or it might just be perhaps a trig substitution that gets applied twice. Or we could consider another option. Could we consider converting this to polar? I mean, let's think about that. In polar coordinates, we would have to worry about what's going on with theta and what's going on with r, and then we also have to think about what's going on with the function itself. Well, let's see how difficult that might be. Perhaps I even planned it to be that way. It's recorded. Probably planned a little bit. Polar theta from 0 to 2 pi all the way around literally the circle. 0 to 2 pi. The radius constant of 2 only, 0 to 2. Please recall that if you are dealing with shapes that especially are circular in nature, polar coordinates give the best boundaries for the region of integration. Can't guarantee that the function will want to play nicely, but if you consider this 1 plus 4x squared plus 4y squared for just a moment, and you factor out the 4, maybe we have an aha moment. X squared plus y squared is r squared. 1 plus 4r squared. That would be the function in the root. Now, let's just slide this up a little bit and see what happens with our calculation if I want to go a little bit further. Right. I need to show that. There we go. So the surface area becomes 1 plus 4r squared is the function inside of the root that, oh, wait a second, dy dx converts to r times dr d theta, and theta goes from 0 to 2 pi, and r goes from 0 to 2, and even though this maybe looks like something that doesn't have an integral possibility that's on the friendly side, we have an extra factor of r, and if you let u equal to 1 plus 4r squared, then du is 8r dr, and I have r times dr. I just need a factor of 8. So I'm not going to do this part very quickly. What I'm going to do is sort of put the picture behind me for a moment. I'm now out to integrate this following problem. 1/8 from 0 to 2 pi. This is u to the half power. The integral of that's going to be u to the 3/2 power divided by 3/2, or multiplied by 2/3 d theta, and r goes from 0 to 2. Those are my limits or boundaries on the r variable. If r equals 2, 2 squared is 4. 4 times 4 is 16. 17 to the 3/2 power. If r equals 0, be careful here. If r equals 0, you don't get 0. So we just have to make sure to include that thought. Let's see, 1/8 times 2/3 is going to be 1/12. 0 to 2 pi. And what do I have here? That was 17 to the 3/2 power. Remember, you do have a pause button if I'm moving too quickly. r equals 0. 1 plus 0 is 1. 1 to the 3 halves is just 1. And because this is a numerical value, it is a constant. Constants can factor out. I get 1/12. 17 to the 3 halves power minus 1. And then the integral of d theta is just theta. And theta goes from 0 to 2 pi. Now if theta is 0, I get 0. But if theta is 2 pi, I get something more. And that's a 2 pi. So I don't know, how shall I write it? Let's write it a little bit farther up the screen. 17 to the 3 halves minus 1 multiplied by 2 pi. And it does reduce. I mean, 2 over 12 is 1/6. Pi over 6 multiplied by 17 to the 3 halves minus 1. And if you want to show units, I never provided units in this problem. I mean, you could say units squared. You could write square units. My rule of thumb in my classroom is if I don't provide units, I don't expect to see units. But a lot of times you've been instructed to fill in your own generic value. So if you feel like you'd like to do that, it is an area. And there you have it. A surface area that sets up pretty easily and turns into something more interesting and is not difficult to evaluate. Well, relatively speaking at least. Hope you enjoyed this, or at least I hope it was beneficial. Until next time.